Hello, my name is TTJ Kepsi Richard. Welcome. Please, have you subscribed to my YouTube channel yet? If no, do. It is the only way you can help me promote my YouTube channel so that I can record more mathematical content for you. Today, our discussion on calculus of several variables will be on a very important theory in calculus known as Euler's theorem of homogeneous functions. Before the video will end today, we will look at what Euler's theory of homogeneous functions says. Then, we will try to determine the homogeneity of some functions, of course, depending on several variables, using the Euler's theory of homogeneous functions. This will be a very interesting engagement, I promise you. So please be my guest. So, Euler's theory of homogeneous functions states that a function which is dependent on two or more variables, so this function dependent on x, y, z, is said to be homogeneous to the nth degree if for all values of the parameter lambda, f of lambda x, comma, lambda y, comma, lambda z, is equal to lambda exponent n f of x, y, and z. So this is what it states. So what that this means to a layman? It simply means that when any function is given to you, introduce a parameter lambda to affect all the independent variables of the functions. Then try to factor out a common parameter of lambda. If you do, when you are able to obtain the function back, then that function is homogeneous. If you are not able to obtain the function back in its original form, then the function is non-homogeneous or not homogeneous. So that's what Euler's theory of homogeneous functions states in a layman's term. Now, we'll take some functions. Using Euler's theories of homogeneous functions, we'll try to determine their homogeneity. So let's look at our first example. It says show whether or not the function f, which is dependent on x, y, and z, equal to x squared plus y squared plus z squared is homogeneous. If homogeneous, state its degree. So one thing we must know is that when a function is homogeneous, it will have a specific degree. But if it is non-homogeneous, the degree will not be known. So the question is saying we should determine whether the function is homogeneous. And if it is homogeneous, we should state its degree. So we are going to borrow the idea of Euler's theories of homogeneous function to determine this. So what is the function? The function f of x, y, and z is equal to x squared plus y squared plus z squared. So what is Euler trying to tell us? Euler is trying to tell us that we should introduce a parameter lambda to affect all the independent variables. So f of lambda x, lambda y, lambda z. So that means any place we see x now in the function, we substitute lambda x. Any place we see y, we substitute lambda y. Any place we see z, we substitute lambda z. So we are going to have lambda x all square plus lambda y all square plus lambda z all square. So when we solve this, we get lambda square x square plus lambda square y square plus lambda square z square. Now, after we do that, we try to factor out the common parameter lambda. So you see we have lambda square, lambda square, lambda. So we can bring it out. So we say lambda square out. We'll be left with x square plus y square plus z square. After we factor it out, ask yourself, did you get a function back? Look at the function. Yes, we have gotten the function back. When you get a function back, then the function is homogeneous. So we said, therefore, the function is homogeneous. Is homogeneous to what degree? The degree of lambda here. So to the second degree. Or it is homogeneous to degree 2. can see that 2 degree 2, the same thing. So this is it. It's not anything difficult. Just introduce a parameter lambda to affect all the independent variables. Substitute. Try to factor out the common parameter lambda out. If you get a function back, then the function is homogeneous. We'll solve another example for you to get a concept. So having gotten the concept, I hope you can do this. So please pause the video and try to see if you can solve it. After that, you compare your answers with mine. It says show whether or not the function f, which is dependent on two variables, xy is equal to x squared plus xy, is homogeneous. If homogeneous, state its degree. Okay, so what do we do? Remember the function f dependent on x and y is equal to x squared plus xy. So Euler is saying that we should introduce another parameter lambda to have lambda x, lambda y to affect the independent variables. So now, any place you see x now, we substitute lambda x. Any place you see y, we substitute lambda y. So we have lambda x all square plus lambda x times lambda y. So what are we having here? We have lambda square x square plus lambda x times lambda y will give me lambda square xy. What's common now? Lambda square is common, so we'll bring the lambda square out. Then I have x square plus xy. After I factor out the common parameter lambda, did you get a function back? The answer is yes. If so, then we can say the function is homogeneous. With which degree? That's the degree of lambda. The degree is 2. Therefore, we say that the function is homogeneous with, you can say that with degree 2. I hope you get that. This is very simple. We'll solve more example on this so that you'll be well cooked in it. So let's look at our third example. It says show whether or not the function f, which is dependent on two variables x, y equal to x cubed plus 2y squared, is homogeneous. If homogeneous, state its degree. So very interesting one. Immediately we see that we are going to use the Euler's theories of homogeneous function to determine that. So our function, which is dependent on x and y, is equal to x cubed plus 2y squared. Now, Euler is saying we should introduce a parameter lambda to affect that. So we get, any place you see x now, we substitute lambda x. Any place you see y, we substitute lambda y. So we have lambda x cubed plus 2 lambda y squared. What happened? We solved it, we simplify this. We get lambda cubed x cubed plus 2 lambda square y square. What's common here? Lambda square is common, so we bring it out. So lambda square out. We'll be left with lambda x cubed plus 2y square. The question is, did you get the function back? The function is x cubed plus 2y square. After we factor out lambda square, the common parameter lambda square, what is left? We are left with lambda x cubed plus 2y squared. It's not the same as that. So immediately you see that means the function is non-homogeneous or is not homogeneous. So we just conclude the function is not homogeneous. As far as it's not homogeneous, then it will not have any degree. I hope you get that concept. So let's solve some more again. Our fourth example, they say determine whether or not the function f of x, which is dependent on xy, is equal to 1 all over x squared plus y squared, is homogeneous. And if it is homogeneous, state its degree. So how do we do that? Please, you can pause the video and try your hand on it. After that, you compare your answers with mine. Now, compare your answers. So we have the function be f of xy equal to 1 all over x squared plus plus y squared. What do? We introduce a parameter lambda according to Euler. So like that. And it will be equal to, that means any place we see x now, we substitute lambda x. Any place we see y, we substitute lambda y. So we have 1 all over lambda x all squared plus lambda y all squared. What do we have? We have 1 all over lambda square x square plus lambda square y square. What is common here? Lambda square is common. So we have lambda square common. We factor it out. We'll be left with x squared plus y squared. See this thing. We can rewrite it in another form using indices as lambda exponent negative 2 times 1 all over x squared plus y squared using indices. I hope you understand that. So the question is, did we get a function back after factoring out the common parameter lambda? Look at the function. Yes, we got a function back. So as far as we get a function back, then the function is homogeneous. To what degree? To degree negative 2. I hope you get that. So we conclude that the function f of xy equal to 1 all over x squared plus y squared is homogeneous. Is homogeneous with degree negative 2. I hope you get that. This is very simple, and I know that you understand this. So our next example says that determine whether or not the function f depending on x and y equal to x minus 3y all over x plus y is homogeneous. If homogeneous, state its degree. So please pause the video and lay your hands on it. After that, you compare your answers with mine. So what does it say? So remember the function f depending on x and y is equal to x minus 3y all over x plus y. What is Euler trying to tell us? He said we should introduce a parameter lambda to affect the independent variables. So that means any place we see x now, we substitute lambda x, and y we substitute lambda y. So we have lambda x minus 3 lambda y all over lambda x plus lambda y. What is common at in the numerator? Lambda is common. We bring it out. We'll be left with x minus 3y. What is common here? Lambda is common there again. So lambda out, x plus y. We can rewrite this using indices. Remember the degree of the lambda here is 1 and the degree here is 1. And remember when two indices are multiplied or are divided actually with the same degree, we will just repeat one of the base. With the same base, we just repeat one of the base and subtract the exponent. I hope you know that. So we'll rewrite this as lambda 1 minus 1 bracket x minus 3y all over x plus y. So what are we getting finally? 1 minus 1 is 0. So we have lambda exponent 0 bracket x minus 3y over x plus y. So after we factor out the common parameter lambda, did we have the function back? That's the question. Yes, we have it back. As far as we have it back, the function is homogeneous. Now, to what degree? Since it is homogeneous, the degree of lambda here is 0. I hope you get that. So we say that the function f, which is dependent on x and y, equal to x minus 3y all over x plus y is homogeneous with which degree? With degree 0. I hope you get that. Please, we'll solve one last example on this so that you'll be abreast with the concept. So, we are going to solve our last example on this. Please remember to subscribe to my YouTube channel if you are here too. like, share, and comment. Determine whether or not the function f, which is dependent on two variables x and y, is equal to x exponent 4 y squared sine inverse of x over y is homogeneous. If homogeneous, state its degree. So how do we do this? So what's the function? The function is equal to x exponent 4 y squared sine inverse of x over y. So we are going to borrow that theory, Euler's theory, which says that we should introduce the parameter lambda to affect the independent variables. So what are we having? We have lambda x exponent 4, lambda y square, then sine inverse of lambda x over lambda y. Now what do? We simplify. So we have lambda exponent 4 x exponent 4, lambda square y square, sine inverse of lambda x over lambda y. Now what is common? You can see that lambda square is common here. Let's try to bring it out. So lambda square will be left with lambda square x exponent 4, then y square sine inverse of lambda x over lambda y. This is an angle, so we don't try factoring out. Now what happens? After I factor out, check whether you got the function back. This function and this, are they the same? No. As far as they are not the same, then we say the function is not homogeneous. And if it is not homogeneous, it will not have any degree. So we say the function is not homogeneous. I hope I've opened up your mind on how to determine the homogeneity of a function using Euler's theories of homogeneous function. We'll end it here today. My name is Titiji Kepsirich.